Okay, so welcome everybody to lecture 2 of this week. Today's topic is mostly about spatial analysis, so closely related to what we talked about yesterday, different ways of analyzing health data in terms of study design, study methodologies. So we're kind of building on that, but specifically today, we're focusing on spatial analysis and how you can analyze these different health trends specifically by location. So that's going to be our focus for today. But we'll start with a quick recap from what we talked about yesterday. So we covered a lot of ground yesterday. Hopefully you didn't find the information that we covered too overwhelming. But to sort of sum up the key things that we discussed, we covered associations, specifically associations between exposures and outcomes, so 2 variables there, and how those associations can offer some clues about causal relationships, about causality specifically. We talked about the Bradford-Hill criteria and how this criteria can serve as a sort of guide or provides a systematic way to compare different study designs or compare how those designs talk about their results, how they talk about their associations that they find in the studies. Now, we also talked about how not all study designs can actually prove cause and effect. They can't all prove causality. Does anyone want to remind us what are the 3 sort of criteria that we need in order to suggest a causal relationship? There were 3 things that we look for. Who wants to refresh our memory from yesterday? Association was 1, yep. Association, time, direction. Yep, exactly. Or time can also be called temporality. They mean the same thing. Great. Now, who wants to refresh our memory in terms of which study designs can actually more definitively prove cause and effect? Which ones can tell us something about a causal relationship? Yep, so RCTs, which are a type of experimental design, and the cohort. The cohort can also suggest a causal association because of the temporality that you're able to meet that criteria with the cohort. Great, so you guys remember all of that from yesterday. If I were to test you on it today, you guys would all get an A+, right? Another sort of important thing that we started to talk about was well, if not all study designs can prove cause and effect, some of them are more so trying to characterize a change in risk, specifically the risk of the health outcome. So they might be trying to say whether exposure to something results in an increased risk of developing some outcome, maybe a decreased risk if it's a negative association. And so we also defined what we mean by health risk. So health risk is specifically related to the chance or the likelihood or the probability that something will actually impact your health, right? It's the risk that some exposure poses to your health. So with all of that in mind, why are we spending so much time focusing on these research methods? We covered a lot of ground yesterday. We'll cover not as much today. Hopefully it should be a shorter lecture today. But in sum, essentially, there's a lot of information out there. You guys have probably become pretty adept at looking things up online. You probably know how to do all that. But as you may have noticed, it's also pretty easy to misunderstand or misinterpret evidence. In fact, we're seeing a lot of that happening these days with information about things like the COVID vaccine or masking policies, stuff like that. So it's really, really important to be able to actually learn how to read studies. Health studies specifically can be really confusing if you don't have that kind of research background. So being able to understand their methods, how they are reporting their results, and how to actually interpret their findings is going to be a really, really useful practice for you, not just through this course, hopefully, but as you go on in your life. So this will be especially helpful for any of you who maybe see yourselves having a future or a career in health policy, maybe environmental hazard regulation, anything like that. A lot of jobs out there have to do specifically with being able to synthesize information from different studies and really being able to apply what you learn from academic research. So hopefully you'll find it to be interesting and useful as you go forward. Now, is assessing a risk to health the same for a population as it is for an individual? What do you guys think? Would it be the same? Would it be different? How might it be different if you think it's different? Any ideas? So Cassandra says different exposures and experiences overall. Yeah. They're different based on proximity to health risk. Yeah. Manan offers a different perspective. So no, because the cause factors contributing to it can be different. Yeah, so many of you are on the right track. If anyone else wants to offer a response, I'll give you some time to do that. Does anyone think that they are the same or that they would be quite similar? Anyone want to offer a difference of opinion? Well, we'll talk about that. So in health geography, we mostly assess risks at the population level, as you may have noticed. A lot of the study designs that we talked about specifically enlist groups of individuals as study participants. So they're interested mostly in assessing those risks to health at a population level. Now, when we do that, we're really providing an average estimate of the probability of some disease happening in that population, in that group of individuals. So by doing that, you're making certain assumptions about the individuals that make up that group. We also, it's worth noting that we're talking about this at certain scales most of the time. So we're talking about populations at a global scale. Especially in this course, we will touch a lot on global examples of diseases that take shape on the global scale, but also national, provincial, and so on and so forth. So risk can be thought of as operating at many such different scales and many different populations. Now, the reason that they are quite different, so for those of you who were thinking that you would assess them differently, you are on the right track there, because risks to individuals are actually quite a bit harder to assess. Why is that? Why do you guys think we would have trouble talking about individual risk? A lot more detail. Yeah, so an individual might be a little bit more complicated to really understand than a population as a whole. Some people may be significantly more susceptible to something. Yeah, that's a very good point. Chronic illness, genetics play a part. Yep. So you guys all have some really great ideas there. There's more variables overall. Yeah. So you guys are definitely on the right track there. So think about it from this perspective. Lots of people smoke, for example, but not everyone who smokes will get lung cancer. There are certain individuals who are going to be more susceptible to develop lung cancer, right? Their risk will be increased due to some sort of personal risk factors, whether that might be some genetics, whether they're also exposed to secondhand smoke, for example, right? So a lot of individual factors actually do end up playing a pretty big role, even though as a population, you might belong to a population that has certain characteristics that might make you more likely. So it is a little bit nuanced there, right? you can certainly try to assess an individual or assess a risk at the individual level, but generally it's easier to make assumptions about populations as a whole because of those characteristics that they share. Individuals can be a lot more complicated. So if we're limited to examining risks mostly at the population level, especially when we talk about the context of health geography, well, how do we actually classify a population? What kind of characteristics do we use? What do you guys think? What kind of characteristics might we use to group individuals together into populations? You could classify them by scale, yeah, so by different geographies, by age, certainly, gender, income. Yep. Yeah, you guys all have the right idea. Socioeconomic status, absolutely. Great. So yeah, I've put up a few examples here that I think most of you touched on. Education is another one, yep. So certainly demographic factors are often used to classify populations. So age being a pretty big one, especially because age is such a significant risk factor for a lot of diseases, right? Older individuals do tend to have an increased risk of developing many, especially chronic illnesses. Socioeconomic characteristics as well, place. So relevant to geography, you could potentially group people based on their type of living situations, so whether they lived in an urban community versus a rural community, things like that. Health status is another really important one that you might see, especially when you're thinking about the context of comorbidities, so people who have more than one disease. If you're trying to study their risk of developing some other disease, you want to make sure that you know what kind of diseases they might already have, because it might influence their risk for developing other diseases. And then this other characteristic, location. So someone mentioned scale, and yeah, that's definitely one that you would also potentially encounter. And so we will focus a lot of today's lecture specifically on this idea of location. So how distance or proximity to some spatial feature, some geographic feature of interest can impact population health risks. So that will be the main topic for today. Now, how do we actually take location into consideration when we're examining disease patterns? We know that location to a hazard or an exposure can impact a population's risk of disease, but how do we actually take that into consideration? How do we actually use that information? Well, as many of you might guess, we like to use maps in geography. So we'll talk about that next. So maps are really, really useful when you're studying diseases, disease transmission in the context of geographic variables, because it can really highlight point sources that are causing some sort of disease in an area. And this is especially useful if you know where those point sources are. So in the map there that you see on the slide, these are points, the red dots are signifying points that are what's known as a Superfund site. Has anyone heard of a Superfund site in the States? Do you guys know what those are? Maybe someone's discussed them in another course. Maybe you've come across them in readings. Does this ring a bell to anybody? Superfund site? I won't ask you what it is if you don't, so it's fine if you say that you don't know. We'll spend some time explaining it. A polluted location, yeah, essentially, yeah. So a Superfund site is specifically where hazardous waste was dumped by often some sort of industrial polluter, some sort of company, and this happened all across the states throughout sort of the early 20th century, because prior to there being any sort of environmental legislation to stop that action, you know, there was nothing to say that polluters couldn't just dump their waste wherever they wanted to, especially in waterways, in sort of abandoned fields. They did it quite frequently. Now, I mention this because there was one particular sort of example that really captivated the national interest in the States, but that also inspired many of the environmental movements globally, including here in Canada. So this was a community called see if I can get the picture, a community called Love Canal. And this was located in New York State, actually close to Niagara Falls. So around the corner from us here in the GTA. Now, what happened in Love Canal was that a company there polluted the ground. They left a bunch of hazardous waste that they buried underground. And at the time, they didn't think much of it. It was the 1940s, 1950s. Nobody was living there. It was essentially these abandoned kind of lots. So they didn't see any issues with burying their hazardous waste there. But fast forward a couple of decades post World War II, New York State, and specifically the city of Niagara Falls, was looking for land to develop more residential places, right? Places for people to live. And so what ended up happening? Well, they sold this land to the city. The city built houses there, and you can probably guess what happened next. So within a couple of decades, by the 1970s, especially kind of late 1970s, early 1980s, it was discovered that a lot of this hazardous waste was actually resulting in some health impacts on the residents there. And so, you know, cases of leukemia, cases of asthma, especially among children, really went up in this community. And so it highlighted just how important it would have been to know where such a hazardous site existed, that maybe they could have prevented so much of this sort of headache that erupted later on because of what had happened here in Love Canal. Thanks, Regina. See you later.
No problem. Have a good lecture, guys.
Thanks. So, you know, what did they learn from this experience? Well, that it would have been really useful to have a map like that to show them maybe we shouldn't build on top of a site like this where you do see significant environmental damage, because we know that a lot of pollution can actually have significant impacts on health, especially if residents are living there for, you know, years and years, potentially decades. So since then, the labeling of these types of Superfund sites has been much more common. In fact, there's legislation that forces polluters and governments to track where these places exist all across the states. Luckily, there isn't really a similar equivalent in Canada. There is certainly tons of industrial waste sites all over the country. I don't want to say that we have pristine landscapes all over Canada, but the sheer volume of these types of hazardous kind of waste sites just isn't really the same here in Canada, luckily. So another thing that we use health maps for would be to highlight the proximity or the distance between certain features. So what I mean by that, here you can see in the figure a map of different highways, and this is a map of Detroit. Now the highways are kind of highlighted with what we call buffers. So if any of you have taken a GIS course, or maybe you're planning on taking a GIS course in the future, you might know what a buffer is. And so it's essentially just this range of distance that covers the outer boundaries of these spatial features. In this case, it's a highway. Now, what they did in this study was that they were interested in studying those black little points, which signify children's addresses, so residents that they enlisted in their study, and they wanted to know what their distance was relative to their address and their distance to the highway, their proximity to the highway. And I believe this was specifically for a study that again looked at rates of childhood asthma. So maps, we learned, are good for highlighting point sources, but also for proximity. What else can they be used for? We discussed this a little bit the other day when we talked about descriptive studies, but maps are also really good. So someone had a question, is GIS needed for health and geography field? That's a good question. It's not needed, but I think in this day and age, it can really help you set yourself apart. If you have certain kind of spatial analytical skills, I think there's definitely a growing need for people like that in kind of the broad health geography research field. So certainly if you have an interest in that kind of stuff and you're already starting to wonder, will I be able to find a job in this? I think the answer is definitely yes. And feel free to kind of nag me about this later on if you do want to chat about what some of the things I bring up during the course of a lecture mean in terms of future careers or where this could lead you. So definitely keep those kinds of questions coming. So this was a third example. So maps can also help us talk about the distribution of diseases, specifically how the rates might look across different countries. So this is an example of a descriptive study. This is what we talked about in the last lecture, or I guess last week. So malaria cases here are mapped, and they're mapped across different African nations so that it shows you what the incidence rate is across different nations in Africa. And it clearly highlights that some nations might be more at risk because the incidence rates are higher there. Now, finally, a fourth sort of example to highlight just how useful maps could be would be for the purpose of risk modeling. Now, what is risk modeling? Essentially, we talked about in the previous example, mapping health rates, so rates of some sort of disease, but you could also flip it. You could map the actual sort of distribution of the hazard. So instead of the distribution of the disease, the distribution of whatever environmental or geographic contaminant might be of interest. So in this particular example, you can see that this is a radon potential map. Now, radon is a really, really interesting sort of example because it's a gas. It's also located in the soils or in the ground of many, many places all across Canada. And radon is a known risk factor for lung cancer. It can cause, especially in people who smoke, a significant increase in their risk of lung cancer if they are both smokers and exposed to radon. And people are exposed unknowingly if they happen to live in a lot of places where radon might exist because it comes through the basements, it comes sort of through underground exposures that you might have. Now, mapping radon is no simple feat because two neighbors could live right next to each other and one house could have radon underground and one could not. So it's really, really dependent on the distribution of the soil and what kind of house you might have as well, because if you have a house that is really well sealed, it doesn't really have any cracks in the foundation, then you're probably going to be significantly less at risk. But so this is kind of a useful practice for other geographic analysts to do because we want to know where places might be more at risk of having this potential problem of radon in the ground. And so scientists will often do risk modeling to understand, well, if you live in this part of, let's say, Saskatchewan, you'll have this level of increased risk of potentially developing something like lung cancer because of what we know are the likely kind of soil conditions that exist there. So that is one other example. Now, can maps be used to establish causality between location and the health outcome? So in this particular sense, when we're talking about maps, we're talking about location being the exposure variable and then the health outcome being the other variable. So what do you guys think? Can maps be used to establish that causality between location and health outcome? So Cassandra says it can suggest it, but maybe not establish it. Okay, does anyone agree? If you can identify a hazard that is location-based. Sydney says, I think correlation, but not necessarily causality. Okay, does anyone else want to offer another opinion? It can illustrate a health risk. Okay, good. So we have some variety of answers here. Well, the answer is no. So we talked about those three sort of criteria, right? We need association, yes. So you can establish association with a map. You can establish that kind of correlation link, as I think it was Reed who mentioned. But that doesn't necessarily mean that you have a causal relationship because as we learned, we need both temporality and direction. And again, the temporality is kind of the thing that's really hard to establish, especially with something like a map, because you don't know whether that geographic feature existed there before whatever health outcome. You would have to do other sort of research to really find out for sure whether there was a time difference there between the exposure and the outcome. But that's not to say that health maps or spatial analyses are not useful. In fact, they're really, really useful. We saw 4 examples there of how they can still be really helpful in order to learn things about the location and about what potential risk factors might be associated with those locations. And one other example I wanted to illustrate was probably one of the most famous examples of a health map being used, and this was Jon Snow and the cholera outbreak that happened in London. So some of you may have heard this example before. It is referred to a lot in epidemiology, so apologies if you've heard all about this before and you're not that interested in hearing it again, but we're going to cover it. So what happened back in 1854 was that there was an outbreak of cholera, which at the time was pretty common in many cities, especially cities the size of London. And this was because of, lack of sanitation, a lack of proper sewage systems in place. And so what happened was that there was a cholera outbreak in this particular neighborhood of London called Soho. So what did Jon Snow do? He was a doctor and sort of an epidemiologist, although at the time we didn't really have this field of epidemiology, so he would have just called himself a doctor. But what he did was that he used a map in 2 very important ways to solve this cholera epidemic. So the first thing that he did was that he mapped out people's addresses. He mapped out where everybody lived who had cholera in that neighborhood. And so that's signified with those little sort of black squares. These are meant to represent the various little houses or buildings where people lived. So every one of those black squares is a case of cholera. So that's the first thing he did. The second thing he did was that he mapped out each pump, every water pump where residents were likely to get water from in that neighborhood. And so why did he do that? Well, he already had this sort of hunch that water was the culprit, that he noticed a lot of the people who got sick mentioned something about drinking water from specific pumps. So this was sort of his tip off. So what did he find out? Well, after mapping, right, he used a map in order to come to this conclusion, in order to make this association. So he found that the pump, specifically in this red square, was the pump that everybody seemed to be using if they lived in one of these addresses where there was a cholera case. So bingo, he kind of made the connection there. And these other sort of red ovals signify the other water pumps that were in the neighborhood, but that people didn't say that they used because they were out of the proximity of where they lived. So that was a really, really important clue. You can actually go and visit the pump in London. Yeah. So this has turned into a pretty big tourist attraction, especially for kind of science nerds or health nerds. Anyone who has an interest in epidemiology would definitely try to make the pilgrimage to London to go see that pump. But so how did he know for sure that this was the association that he kind of had a feeling was there? He ended up removing, or he asked the city to remove the pump's handle so that people could no longer use the water from that pump. And what happened? Well, miraculously, the cholera epidemic kind of subsided, the cases plummeted in that neighborhood, and it was no longer really an issue. So what did he learn? Despite there not being even a germ theory at that time, right? He didn't even know that it was a bacteria that was causing this sort of outbreak of cholera, but he learned that just through some very good map making, you can actually solve a health geography kind of dilemma like this, right? A localized health threat in a particular neighborhood. So it was very useful from that sense. Now, what did future epidemiologists learn from this? So again, they learned that maps can help you identify pollution point sources that are impacting the health of, let's say, residents in a neighborhood, for example. Maps can also display patterns in infectious diseases and how they spread across various locations. And they can help you really contrast the burden of diseases across different areas, especially on the global scale. You can compare incidence rates from multiple nations and get a sense of what the burden of a disease is, let's say, across an entire continent. But importantly, maps have some limits. They have some limitations. So number one is that there's some privacy issues. What Jon Snow did back in the day, we could not really do anymore. We can't map out individual cases of diseases that could be potentially identifiable. This is because we would run into some privacy issues, especially related to rare diseases. So if you know that there's only 2 cases of some really rare disease, it would be potentially quite problematic. What does the term burden of disease mean, specifically in our context? Yeah, no, that's a great question. So the burden of disease we talked about in, I think it was the first lecture, but the burden of disease is essentially quantifying the full extent of some disease. So usually it's summing mortality, morbidity, and some sort of economic costs. So it's just the sum of some health indicator, whether that's mortality data or disease rates or economic rates. Sometimes it combines all 3 of those things into some sort of giant sum of the true extent of some disease. So that's the burden of disease. Some other limits of maps, though, are that it is hard to map trends over time, right? You would need a series of different maps to show different things happening over the course of years, let's say, because you can't really use a graph the way that you would a map. Some other limits is that you need some way of capturing the collections of this kind of data, especially if you have, let's say, a large database of health data, health records. You need some way to actually graph that in a map in order to display the trends. So we'll talk about that. So some common spatial analysis techniques. How do we actually use data in a map form? Well, the first way would be to aggregate the point data at some scale. So in this example map, it's the city of San Francisco, and their police department took data that was individual level kind of crimes that happened at various geographic locations, right? So each point represents a crime that took place at that location. And what they did was that they aggregated those little points and they aggregated them into the police department divisions so that they could understand what the trends were in terms of the total crimes per police department. So they did a very sort of simple aggregation here where they just summed all the point data into these sort of geographic areas or these polygons. Now, another way of doing that would be aggregating point data into rates. So instead of just summing the point data, you would actually turn that into a rate. So the sum per some unit of analysis that you're interested in. An example of that would be this map. So this is a map of asthma incidence rates per local health integration network. And that's just sort of a fancy term for these hospital networks that exist in Ontario, and they're regional based. And so you can see clearly from the map that the GTA areas have particularly high incidences of asthma. So this sounds really, really useful. Aggregating point data into a map form seems to be a really awesome way to look at these trends. But what could go wrong? What issues could arise from that? Well, the first issue is called the modifiable aerial unit problem. Now, depending on how you actually aggregate that data, certain boundaries can lead you to make some pretty biased interpretations of potential associations that may or may not actually be there. So what I mean by that is that, think about it from this perspective. In this region A, let's say this first square, depending on how you draw this circle, if it's a really big sort of quarter of a circle here, you could encompass multiple illnesses. But let's say you drew the circle differently. Let's say you drew a smaller circle. You might not capture the one case of the illness here. So the scale of the area, the extent or the size of the area is something that really impacts what your rate of disease will end up being. How many cases of a disease will end up being captured in that particular geographic area that you're looking at. So that's one, size or scale. The other thing that really influences this problem is the shape of the polygon, right? So again, depending on how you draw this boundary, whether you use a straight line, for example, whether you use a circle, it can really impact, again, what that final rate will be just based on how you draw the line. If you draw the line neatly around each of the disease cases, it'll obviously impact what the rate will be in that particular geographic area. So that's one problem, the modifiable aerial unit problem. The second issue with this kind of aggregation of data is something that we call the small numbers problem. So small areas, small geographic areas are especially prone to this type of issue, and I'll illustrate why that is. Let's say you had 2 cases of some really rare cancer that happened in this particular neighborhood of Hamilton called Beasley. Let's say you had 4 cases of the same really rare type of cancer that happened in the next door neighborhood called North Industrial. Well, if you were just looking at these numbers, you would say, okay, 2 cases, 4 cases, there's only a difference of 2, right? 4 minus 2 is 2. But if you were to turn this information into a rate, the difference in the rates would be a doubling in risk. So that's a pretty big discrepancy because the numbers are so small and the areas are so small. So this small numbers problem really happens when there's small sort of numbers at play and the differences between them might appear larger than they actually are based on how you then turn the numbers into rates. So that's another kind of important issue to be aware of anytime you're looking at a health map. Now, what are some potential solutions? How do we address these things? Well, one way would be to expand those geographic areas, right? That's why we tend to avoid doing maps or health maps at the neighborhood level because it's so prone to these types of issues, these types of small numbers problems especially. Another way to do it would be to extend the time period of the map. So instead of looking at only 1 year, maybe you would look at a 5-year period and you would sum all the cases of that disease over the course of that 5 years, just so that you collect more cases to actually map out. But another sort of issue to be aware of here would be spatial autocorrelation. So what is that? Well, you might notice on this particular map of China, this is a map of the cases of altitude sickness among tourists. So if you were just looking at this map and you had no other contextual information, you didn't really know what else was going on, you might say, that's odd. There's, these 2 clusters, these 2 dark areas on the map that seem to have a lot of cases of this particular illness. I wonder what's going on here. But because of this issue of spatial autocorrelation, you might ascribe meaning just because these areas of focus are close to each other. So you might think that there's some sort of, factor here at play, some nefarious factor here at play causing this increase in cases. But what do we actually know is happening? Well, does anyone know sort of the geography of what is in that part of China? What sort of geographic or geological features rather are in that part of China? Mountains. Yes, exactly. So that part of China is the Tibetan Plateau, right? So it's close to a lot of mountains, and in general, the altitude of that region is significantly higher than other parts of China. And so it absolutely makes sense that altitude sickness cases would be higher there. It's not because of some other sort of external factor leading to an increase in disease rates there. So that's all that spatial autocorrelation is saying. It's basically when you accidentally ascribe sort of too much meaning to a particular relationship or what appears to be an association on a map, which could easily be explained by some other factors that you're not looking at or maybe not aware of. So this brings us to an interesting case study that I wanted to present just to sort of bring attention to how we actually might assess health risks in a spatial way. Because despite these types of limitations that we've described, disease maps are still really useful and we can still learn a lot about them, especially from the context of a descriptive health study, right? The whole point of these types of studies is just to learn. It's just to get an idea of the extent of what a health issue might be across some sort of geographic area. And so they do still play a really, really important role in health geography. So where is Bangladesh? Well, it's located just east of India for anyone who's not really familiar with that part of the world. And what's interesting is that the people of Bangladesh used to rely on surface waters for drinking water for years and years. But because of issues with sanitation and sort of sewage problems, this area was prone to many cholera outbreaks, like what we saw with London back in the 1800s. So what started out in about the 1970s was that they started to construct wells, well water, all across Bangladesh so that people would no longer have to rely on the sort of polluted surface water for drinking water. Instead, they could just use the wells. And so this was great. By the 1990s, 97% of people in Bangladesh had access to well water. This was seen as a huge success. So as you can see in the graph there, based on this success with the wells, the incidence of mortality went way down, specifically from diarrheal diseases, which are usually associated with contaminated drinking water. So this seemed like a great, success story. What could possibly go wrong here? Well, what they didn't realize was that this part of the world in Bangladesh is also really prone to arsenic leaching in the groundwater. And this happened naturally because the same sort of geological features that made Bangladesh have this abundance of groundwater also led to arsenic sediments coming from the sort of Himalayan mountains to deposit those sediments in the groundwater along with that drinking water. So they didn't know this at the time, but once they finished building all these wells and once people started to use them to get drinking water, it became pretty apparent pretty quickly that in some places up to 80% of the wells that they tested were contaminated with arsenic. And I'm not saying just contaminated, but the levels of arsenic were far beyond what would be considered a safe level for drinking water, especially drinking water that you use for showering, for cleaning clothes, for a multitude of other purposes. So why was this so noteworthy? Well, arsenic has been known to have a multitude of impacts on human health, so they were particularly concerned when they discovered this arsenic leaching in the well water. For example, some acute health effects are things like vomiting, abdominal pain, diarrhea, even death in some cases. The chronic health effects as well are really important to note. So they can cause skin lesions, skin cancer, bladder cancer, lung cancer, as well as respiratory infections and cardiovascular disease. So some pretty nasty stuff that you would definitely want to avoid in a population, especially a population that you were hoping to help alleviate some health impacts from drinking water. So they had this feeling that the arsenic was to blame, but how did they actually link that exposure to the health outcome of various different health outcomes associated with arsenic exposure? That's to say, how did they know if exposure to arsenic was specifically leading to those impacts? Well, they used maps in many health studies. So what you could actually do, similar to what Jon Snow did, was map out the cases of whatever health outcome. In this particular example here on the map, it was respiratory infections. So they mapped out those incidences, and they found that in the sort of red circle there, there was a particularly high risk of respiratory infection. And in the blue circle, they found it was a significantly lower risk. Now, they linked this because in that area, they found higher concentrations of arsenic, right, in the red circle. But in the blue circle, what they also did was that they installed water treatment filtration systems against arsenic to try to clean up some of the well water there. And what they found there was that it actually reduced the risk significantly compared to sort of the no treatment zone. So that's how they were able to establish that link, just by comparing the health outcome, in this case, respiratory infections, and specifically looking at, well, what happens if we treat the water there? What happens? Does it reduce the risk? Does it, impact the risk in any way? And they found that it did. But you might notice that this is a pretty simple way to approach this problem, right? It kind of assumes that everybody in the red circle has the same exposure, right? They're all exposed to some high level. But what did we learn yesterday? We talked about this thing called the dose response. And so they didn't really take into account dose in this particular study, but that is a really important part of establishing whether a health outcome can actually be linked to some geographic feature. So other studies did this. And so how would you take into account that difference in dose? Well, there's a few different ways you could do that. You could monitor the arsenic concentrations in those wells over time, right? So that you get a sense of what the levels actually are. But as you can tell, that would probably be pretty expensive to install concentration samples in every single well over the entire country. So maybe that's not so feasible. Another way you could do that would be to just take a survey of individuals about their duration or the quantity of their exposure. So how much they use the water, how frequently, which particular pumps they might use it for. And then using that survey, you would compare potential disease incidences that way. So another way you could do that would be to compare the characteristics of those who got the disease and those who don't. Essentially, you could run a sort of case control study. So there are many ways to work around this type of issue, right? This issue of dose, because it is something that you want to take into account. But as you can see, it might be quite difficult to implement in practice, especially in the context of such an extensive environmental problem, right? It's essentially the whole country that's dealing with a problem, not just a little neighborhood or a section of a city. So to sort of wrap up today, there are many, many ways to explore how one's location and what people are exposed to in that location influence one's health. And these types of spatial analysis techniques really do tell us about how population health risks vary across different geographies. So they can be really, really useful. But as we saw, they do have some limitations, right? Maps are really useful tools to show these relationships, but they can't really determine any sort of causal links. So you do have to interpret whatever it is that they're displaying or visualizing with a bit of grain of salt. But to sort of sum up for today, health maps are still really great, and they do serve a really, really important purpose in epidemiology and in health geography more broadly. So that's where we'll end things today. Are there any quick questions before we stop? If not, you guys are free to go.